morning to everyone. So, there is a new week and new lecture. I am very pleased to let you know that we have a lecturer, Professor Andrei Starinets from University of Oxford. He's mostly working on application of string theory to strongly interactive quantum field theories in finite temperature and density. As is known, this set of application is known as gauge string duality. First, Andrei's alma mater is Lomonosov Moscow State University. In this sense, he is my academic brother. And I am happy to have him here, especially for this reason as well. And before, later, his borderline has passed through different institutes in the world. Among them, Institute for Advanced Study at Princeton, University of Southampton, Perturbation Institute for Theoretical Physics, Institute for Nuclear Theory of Columbia University, New York University, and some others. Andrei Starinets is a winner of Maxwell Medal and Prize for his contribution to our understanding of the transport properties of system of strongly coupled quantum fields. He has kindly agreed to visit us and give a series of lectures in these very hot and fascinating topics of modern science. Please join me to welcome him and
Thank you very much. Thank you very much for this warm introduction. Our agenda for these 4 lectures will be the following. So today, I will talk about things which are not directly related to holography or ADS-CFT correspondence or gauge string duality as it is known. This will be postponed until Thursday. But today, we'll need to do some preliminary work. And the plan for today will be written on this board. Now, before writing the plan, let me just say very few words about organizational matters. So I understand that all of you received a list of references in the email, right? And you have received it, right? And from time to time in the lectures, I will refer to this list of references in a very brief form. So I will say, for example, somebody like Palczynski, 2010, right? And that means that you will need to do a little bit of work and find in this list of references the name and the date and so on. And if you have any difficulties whatsoever, please do ask me, find me somewhere in the hall and ask me about this or anything else that matters for these lectures. So these are the references. Now, so time, of course, is short for these lectures, so it mostly, I hope it will be mostly motivational and inspirational part rather than the factual part of the story. But please do feel free to interrupt me anytime, especially because I'm still not quite awake after yesterday's flight. So please just raise your hand, and if I don't pay any attention, which may happen, please just shout, interrupt me with your voice, and ask questions. This is essential. Of course, if I feel that the number of questions exceed my ability to answer them, I will do something about it, but don't be shy. That's the point. And also, please do feel free to ask me questions after the lecture and in the middle of our sessions. Okay, so the plan will be the following. So we'll start with introduction and motivation. Then we discuss 2 essential tools. And 2 essential tools will have something to do with generating functional for correlation functions in quantum field theory at finite temperature and density. So as was said already, the topic is hot in the sense that we'll be dealing with relativistic systems at extremely high temperatures and rather large densities. And we will need some tools to explore these subjects, and this will be one of them. We'll talk a little bit about quark-gluon plasma and various models of this interesting object. And in order to describe this object, we will need some introduction to relativistic hydrodynamics. And one of the tools, so this, one of the tools in item 2 will be the set of so-called Kubo formulas, of which there are many, and actually the number is growing with every year. But we will discuss not all Kubo formulas. We'll discuss Kubo formula which we'll need most. And this will be Kubo formula for the shear viscosity, as an example. And by the way, is this visible? Okay, fine. So I won't make it larger, but please do complain aloud if something is wrong. Then finally, we'll understand that in order to compute things we want to compute, and this means thermodynamic and transport properties of the system we are interested in, we will need tools which are non-perturbative. We need to go beyond perturbation theory. Because quantum field theory historically was revolving around the tools which were perturbative. You have Feynman diagrams, you have perturbation theory in quantum mechanics and so on. And this is incredibly useful, except that sometimes you need to say something about the systems which live in the non-perturbative regime, where coupling constant is large or of order 1, and therefore you cannot really expand in small. There's no small parameter to expand. So you need something, you need some tools in order to access this non-perturbative regime. And again, historically, there is a great tool which is called duality, and we'll talk about this in the last 2 lectures. But here today, I want just to give you some simple examples of duality, because duality actually is a rather wide notion. And I also hope that we'll have time today in the second lecture to talk about one particular example, which is known as Kramers-Vanier duality in lattice statistical physics. And again, without too much detail, but we will discuss at least our favorite Ising model. All right, so this is the plan. And let's proceed, unless there are questions. So what I would like to do, I will write things on board, not only formulas, but also words. Because sometimes I had this wonderful experience when you have a lot of formulas and no words connecting them, and after a while, it's impossible to understand what exactly was going on. So I will write some words, not all of them, but some. So the motivation. So motivation is quite obvious. We want to understand physical properties of macroscopic systems based on microscopic description. All right, so want to understand macro properties of physical systems or model systems from the microscopic description, from micro. Or sometimes this is called from first principles. Now, what this means, so I can give you 2 trivial examples. Well, one is trivial, one is less. Example number 1 is water. So we all know that water has microscopic structure. We know what the structure is. And we know if you go sufficiently down the road, right, so of course it's not just molecules H to O, it's also the atoms which make them, right, and then there are also quarks and gluons and God knows what. You go down the scale and you discover all these microscopic ingredients. But sometimes you don't really care that much about the behavior of these ingredients in great detail. You care about macroscopic properties of water. For example, you're solving some hydrodynamical problem, and you know very well that this is described by Navier-Stokes equations, and this description is pretty adequate. So one obvious question is how this description, which is, for example, Navier-Stokes equations, which you can solve for describing the properties of motion of bodies in water or in gas, how these macroscopic equations, macroscopic description, arises from microscopic properties. Or put it in a scientific language, suppose somebody gives you a Hamiltonian or Lagrangian of a particular system, let's say of water. It's fairly easy to write down. Can you derive Navier-Stokes equations from that Lagrangian and write down everything, describe whatever you want to describe at macroscopic level? So this is the approach which is typically known as effective theory approach, right? So you start with some microscopic ingredients, and then you go to the larger and larger scales. And there is some mathematical process which is sometimes unknown. So for water, for example, this is unknown. Nobody knows how to do it. So which actually gives you, which derives you these Navier-Stokes equations, which are adequate for description at sufficiently large distances and sufficiently large times. So this is this is a simple example. So what do we want to know about water? So we want to know, for example, phase diagram and other systems, right? So phase diagram. So we want to know, for example, what is the critical temperature, what is the critical pressure, some things about the structure of ice. Let's say there are different structures of ice at different pressures and temperatures and so on. So these are so-called thermodynamic properties. So these are thermodynamic properties. Right, and there is another set of properties which is essential, and they're called transport properties. Because, so with transport properties, what we mean is viscosity, diffusion constant, some thermal conductivity, electrical conductivity of substance and so on, right? So this is basically all people in who are dealing with concrete systems. This is all we want to know. They want to know a set of thermodynamic properties in great detail with the ability to predict them, and they want to know set of transport properties for the same reason. They want to predict the behavior of this material at sufficiently large distances and sufficiently long times. So what happens is that microscopic description, so micro description, in principle, from the Hamiltonian or from the Lagrangian, is supposed to give you all the information you need about thermodynamic properties and transport properties as well. And the question is how to derive all these ingredients, all these properties from microscopic physics. And for that, there are various tools which we're about to discuss. Okay? If water is not sufficiently strong example for you, you can think about something more exotic. You can think about, for example, atmosphere of some planet like Jupiter, which exists at certain temperatures and very high pressures. And you may remember from your undergraduate courses, right? So let me draw very schematically a typical phase diagram. So typically what happens, so you have in coordinates pressure and temperature, some generic phase diagram where you have a triple point. So here is some line which normally ends or often ends with the second order phase transition, which is known as a critical point. Critical point. And here you have gas or vapor, and here you have solid. Right, and if you think of water, for example, then yes, so there is some line at normal atmospheric pressure, 1 atmosphere, and you cross these two lines of phase transitions. And of course, what you want to understand is how to predict where you cross this line from microscopic physics. And here you have the usual phase transition of melting the ice and then evaporating of, of boiling water. Then there is a critical point, and then there is a region here which is typically called supercritical region. Supercritical region. And you may say, well, that's fine. Suppose we don't know how to predict what is happening here from microscopic physics, but we don't care. We can always do an experiment. This is just water. So why don't we just measure all these properties, in particular the location of the critical point and so on? Now, this can be done. In fact, has been done. But if you are talking about the regions which are sufficiently exotic, so for example, very high pressures, that is rather difficult to implement experimentally. And if you're talking about substances which are rather difficult to access and put into these laboratory conditions, such as, for example, the atmosphere of various planets, such exotic planets or not so exotic planets, then you may want to find out how to do these computations in order to predict at least something. So you can imagine that you're somewhere in the atmosphere, dense atmosphere of a giant planet, and you're in a spaceship and you want to communicate, right? And for that, you need transport coefficient in order to understand, how far your communication will go in this substance and things like that. So what are the tools, right? So in principle, we want this, right? So of course, there are substances such as quark-gluon plasma where these properties are simply impossible to measure in the laboratory in the way that we measure, for example, viscosity of water. So viscosity of water can be measured in a school experiment, but viscosity of quark-gluon plasma is another matter. So this is rather difficult to do. So we need some microscopic understanding of how this happens. So in order to, I can give you some maybe more examples to for motivation, perhaps more exotic. There are some interesting questions of how, for example, resistivity of metals behave with temperature. And I will call them strange metals. Oh, they are called strange metals. Because most metals, as you probably know, are well described by Landau Fermi liquid theory. And if we're talking about usual metals around, then there is a theory which allows you to predict all these transport properties from a microscopic principle. But there are substances where this approach fails. And in that sense, they're called the strange metals. So resistivity is a function of temperature. So typically, it has this growth with temperature. Well, we are talking about the resistivity above the phase transition, above the transition to the superconducting phase. It may happen that resistivity drops to 0, but above this, so suppose there is some region of superconductivity, but then above this region, you have typically dependence which is parabolic. Normally, so rho scales as t squared. This is normal, so to speak. But sometimes it happens that rho scales with other exponent of t, and this is called strange. This is called strange. Now, normal metals are described by Landau Fermi liquid in the sense that this behavior is explained. And nobody knows why, for strange metals, which are of particular interest because they involve substances related to high temperature superconductors, nobody knows why the exponent is different for these strange metals. So this is unknown. And again, the question is, so this, of course, was understood not only within the phenomenological, if you want, approach of Landau, but also from microscopic principles in the 60s, how the Fermi liquid behaves at small temperatures. But here, despite sufficient effort and many interesting ideas, and there is no solid explanation of why this behavior happens as it happens. So this is another question of how you can describe this from microscopic physics and explain why what is happening microscopically, so it gives you this property. So things like that. Now, how about tools? So we need some tools. And tools are rather simple. You know at least one of them extremely well. In order to say anything you want to say about thermodynamics, you need to compute the partition function of a theory. So we will be dealing with this object time and again in various incarnations. And the difference with computing it now, difference from the standard zero temperature quantum field theory calculations, will be that this will be a calculation done at finite temperature. So we want, tools. Thermodynamics will follow from computing free energy, or let me call it omega potential. Omega potential, which is up to a temperature, is the log of the partition function. And our z, the partition function, is trace of the density matrix rho, where rho is, in the Gibbs ensemble, is e to the minus beta h, where h is the Hamiltonian operator, plus, I will write this in this following form, mu a times QA, where QA are conserved charges in your theory. Q dot is equal to 0.
Andrei?
Yep.
Sorry, may I interrupt? If you use the blue pen, there's much more contrast there.
Thank you. Yes, I was worried about that. Yeah, that's a great suggestion. Yeah. Right, so one remark about, so you had seen this, of course, before many times. One remark that I want to make is that in non-relativistic theories, which normally is the subject of statistical physics courses, you will have mu, the chemical potential, so that doesn't look like is it any better? No?
Use the black one.
Use a black one. Thank you. How many colors do we? Yeah. I don't see a black one. Yes, thank you. Yeah. Aha, great. Thank you very much. Yeah, so in non-relativistic theories, we have a chemical potential which is conjugate to a conserved charge, which is the number of particles in the system. So in non-relativistic systems, the number of particles is a conserved quantity, and therefore you can introduce a chemical potential which is conjugate to it. In relativistic systems, normally interacting with relativistic systems, what happens is n is not conserved. Right, we know why, because in relativistic systems, of course, energy can transfer to mass and vice versa. You cannot really say that you have n particles if they all interacting, and you have annihilation processes and creation processes all the time, thanks to E equal to mc squared. So n is not a good conserved quantity, but in relativistic domain. But there are other conserved charges. So for example, baryonic charge or leptonic charge within the validity of particular conservation laws. So in principle, you can have a number of conserved charges such as, so relativistic system not conserved, but we have other charges, other conserved charges such as Q baryonic, for example. Right, and so on. So when we will be mostly talking about relativistic systems, and when I say chemical potential there, it means chemical potential which is conjugate to one of these other charges, not the number of particles. Okay, fine. So then there is another object which we'll need. Yeah. So okay. So we have this object. In principle, we know how to compute Z, and once we know Z, we can compute its logarithm, and therefore you know all thermodynamics, you know free energy. It means that from this object, thermodynamically you can compute anything you want. You can compute equation of state, energy, pressure, entropy, anything you want, including speed of sound, for example, right? So all thermodynamic quantities follow from computing Z. Okay, so this is object number one, tool number one. Yes.
Shouldn't the number of particles n be a large number in order to use this formalized?
No. Here, well, you have to, so you can write this thing in principle for n, which is a finite number of particles, right? Then you have to take so-called thermodynamic limit. Right, so plus finite size effects. So this is a typical, there is nothing here beyond the standard statistical physics, right? So you have a number of particles which is sufficiently large, you fix the ratio of number of particles to volume, you keep it fixed, you take volume to infinity, you take number of particles to infinity, right? And then you have some answer plus finite size effects, which are always there, right? Because the real system, like there is no real phase transition ever. You can never have a free energy which is a function which is actually divergent, right? So nature doesn't know any divergences, but it will go like this. It will go vertically down, almost down, right? In fact, with a slope 10 to minus 26, right? So that's in that sense it is a limit of infinite number of particles. Okay, but you may ask a question of what happens if you have this number of particles which is not so large, and what does it mean to have a thermodynamic limit, and what is large and what is not large. So for example, in systems which I'm going to talk about today, like quark-gluon plasma, the number of participants is about 10,000. Right? And you may ask a question, is it large or not? Is it enough to apply all these things? And what kind of finite size effects you will have? In fact, you may ask even deeper, well, not deeper, but just another question along the lines, when do you start seeing the collective effects when you increase the number of particles n, right? So for example, you have a two-body problem, right? So that will not give you any collective effects, right? You have a wonderful, exactly solvable system and so on. Then you add the third body, right? Then it's not exactly solvable typically, but you still don't see much collective effects, right? You have this Kolmogorov-Arnold-Moser theory, if you have n bodies, right, in mechanics, I'm talking about mechanics. And you can see chaos and so on, and it's a fascinating subject. And then there is a question of what should be this n when you start seeing collective effects. And as far as I understand, the answer to this question is that the number n is not really that large, so that you can actually apply the ideas of statistical physics. So I cannot give you the exact number, but people are doing simulations, and it's not even 10,000. So it's something of the order of 100 or so. So you will see collective effects. So, but yes. So any other questions? Not yet. Then there is a second tool, right? So we'll need this, and then we'll need also some tool to compute transport properties. Okay, so thermodynamics we have dealt with. It's done. Now transport. How do you compute transport? So for example, viscosity. Keep in mind, one parameter, it's easy. So for example, we want to compute viscosity of water from first principles. How do you do this in principle? How can you do this? So in order to do this, you need something which is known as the linear response theory. Linear response theory. And yes, one other organizational thing is the following. So whatever I'm going to say will be often in the form of hyperlinks, which means that I won't have time to explain anything in detail, but I will give you a hyperlink. So for example, if I say linear response theory, I will write a number of formulas. But if you're not familiar with this subject, it means that after this lecture, you go and learn it in full detail, because this is an essential ingredient for any educated physicist, so this is important, right? So if you haven't encountered it before, find the books in this reference list or otherwise and learn it. So linear response theory is a rather simple setup, has a rather simple setup. It tells us the following. So suppose you want transport, let's say conductivity, for example, you want to compute conductivity or viscosity, which is slightly more complicated, but still. So what do? You have a system in thermal equilibrium, And then you want to understand transport properties, meaning how the system reacts if I, for example, create by hand some disbalance of charge in it, right? So suppose by external sources, for example, by external electromagnetic field, I create some disbalance, so I have concentration of charge. I put some concentration of charge which is larger here and smaller here. Just a little bit, not much. I won't disturb the system very much. What will happen? Current will flow from high concentration of charge to low concentration of charge, right? It's a small current, and this current will be proportional, of course, to the disturbance, to the external electromagnetic field, with a certain coefficient, which is our conductivity, sigma. So in order to measure this, or theoretically measure this, all I have to do is to take my original Hamiltonian in thermal equilibrium. So I have a system in thermal equilibrium, and I have it described by Hamiltonian H naught, and I disturb this H naught with a little perturbation which I will call delta H. Okay? And what this means, so delta H here can be written in the following way. So there will be some integral over, let me do it in d dimensions, just to be a little bit fancy, with some, I will explain in a second, t, x, and then there is some operator, let's call it a, which also depends on t and space, and space coordinates. So what does it mean? So suppose that I want to disturb the system from equilibrium by external electromagnetic field. Then this external field is denoted by lambda. So this is what you normally call a mu, but I will need lambda for something else as well, so I just denote it by lambda. And J would be electromagnetic current in the system. Let's say J mu. So I perturb my Hamiltonian with external field, and external field, so you can think of electromagnetic wave, right? Electromagnetic wave, E and B, they will couple to something in the system. And this something in the system will be in the form of the current, right? With the form of, for example, psi, gamma mu psi, if you have a relativistic fermionic system. So this external field will couple to this and induce the flow of current, which I described before, and therefore you can measure conductivity. Or suppose you have a neutral system and you want to measure viscosity. How can you measure viscosity? So what is viscosity anyway? So viscosity is a measure of internal friction in your liquid and gas. So suppose you have flows. So this is a flow of gas or liquid, and you have here some microscopic ingredients, and they flow somewhere with different average velocity. So for example, this layer is traveling faster than this layer and faster than this layer. But because molecules go in all directions, there is some transfer from time to time. There is a transfer of momentum between the adjacent layers, right? So faster molecules of the upper layer will speed up the lower layer, and the slow molecules of the lower layer will slightly slow down the upper layer because they transfer momentum in the vertical direction and they penetrate these layers, and therefore eventually the velocities will equilibrate and everything will be again in equilibrium. So viscosity is a measure of how well this momentum is transferred between the adjacent layers. So this is a measure of internal friction of a liquid and gas. And this is no different from this motion. You have your palms, right, and you do this. And you feel heat. You feel heat precisely because of this friction, because the particles of one layer penetrate the particles of other layer, and they will equilibrate velocities, they will slow down, they generate heat in the process. So, yes, this is shear, exactly, yes, this is shear. There's also a viscosity which is called bulk viscosity, and we will talk about this a bit later. Fine, so how to measure shear viscosity in a neutral fluid? So suppose you have some sample and you want to use this machinery of linear response in order to measure viscosity. If you want to measure conductivity, you apply external electromagnetic field. If you want to measure viscosity, you need to create now not a flow of current from high concentration of charge to low concentration of charge, but you need to create some shear in your sample. In order to create shear, you use a wonderful tool which is called gravitational wave. So you take, so suppose you're almighty, suppose you have you're a great experimentalist, right? And you just generate the gravitational wave in the polarization and shape, whatever you want to generate. So you send this gravitational wave to your sample, and the gravitational wave of particular polarization, it will create shear, it will squeeze, it will do something with your sample, and if you calculate well enough, right, so it will create a shear. And this external gravitational wave should not destroy your system, but it just creates a shear, and then the system goes back to equilibrium, and the response to this external gravitational wave will be a shear viscosity, just like response to external gravitational, external electromagnetic wave is the conductivity. So this is a tool. Now we want to write another formula. So this is just a description of how I set up the experiment. And now the question is, what is the outcome? And the outcome is the following. So you have, so in the expectation value of the operator in question, which can be a current, for example, in our first example, will be proportional with a minus sign to a very interesting object, which is known as retarded correlation function, retarded Green's function, GRAB of t minus t prime, x minus x prime, times lambda b, right, of t prime and x prime. And this retarded correlation function is the object which will need to compute transport. So let me write this in full glory once. So G retarded of t minus t prime, x minus x prime is minus I, Heaviside theta function, and then the average of the commutator of two operators in question. So A, think of A as a current operator, for example, or in case of gravitational wave, same, it will be energy momentum tensor. Okay, closed. All right. Now, in Fourier space, the formula there will look extremely simple. So you have the change from equilibrium of the expectation value of the operator that you are interested in, and it is proportional to the influence to external field in question lambda and the retarded correlation function in Fourier space. So this is tool number 2. It's not clear from this formula yet how to compute, for example, viscosity. We will do this hopefully in 15 minutes. But one thing that I want to say is the following. Of course, if you are not familiar with this formalism of linear response, it's absolutely unclear of why these formulas appeared in the first place.
So actually, this is in linear systems theory. This is like the convolution integral, right? And this is
yes,
the corresponding multiplication in the frequency domain.
Yes, exactly. Yes. So this is just in Fourier space. So we will assume the Fourier transform of the form minus I omega t plus I q x all the time, and that becomes a convolution. So things I want to say is the following. So if you have not seen the standard apparatus of linear transform, please, this is a hyperlink. Go and learn it. You are capable of deriving all this in 2 pages, right? With solid undergraduate education, this is possible. Take any book. So for example, I promised you references. So from the list that I gave you, you can read Le Bellac book and highly recommended lectures by Comrade Kovtun. Not only for this, but for basically everything I will say. This is in the archive, lectures on hydrodynamics and so on, and in particular about linear response. So I won't say much about this, but basically what you're doing is a time-dependent perturbation theory in quantum mechanics. So this can be quantum field theory, or it can be ordinary quantum mechanics. So you have a disturbance of your Hamiltonian by some operator, and then you can, by perturbation theory, you can calculate to linear order. So it's called linear response because you're computing everything to linear order in lambda. So your lambda, your disturbance, your magnitude of your gravitational wave or electromagnetic wave is very small. You may say, how about nonlinear response? I want nonlinear. And it's also possible you can compute corrections to this, but in most cases it won't really be necessary. So this formalism is extremely simple. It tells you how your density matrix rho, which is gone already, this one, responds to this change in the Hamiltonian. Remember, rho was trace e to the minus beta h, and now you have trace e to the minus beta h plus a little addition, right? So you need to calculate how the quantum states change and how rho changes, and then take a trace. And the result is really, really quite impressive. It's very, very simple to derive. It tells you that yes, the change in expectation value of various operators in question will be proportional to the retarded correlation function of this operator, of the commutator of this operator. Now, the brackets here, which in usual quantum field theory zero temperature would correspond to vacuum expectation value, here stand for taking the average in a Gibbs ensemble with the equilibrium rho. Right? So let me write this with brackets T, comma mu. This means that averaging this commutator is happening in the equilibrium Gibbs ensemble with the equilibrium values of the Hamiltonian H naught and whatever charge you have. Okay? Equilibrium. So the moral of the story is the following. So you have your system in equilibrium, you disturb it a little bit, then it goes back to equilibrium, and at this moment you have tools to compute whatever transport coefficients your system has. From first principles, these are microscopic objects, right? So these are operators. So the role of O is played either by J, and this gives you conductivity, or in our most interesting example, the role of O is played by the energy momentum tensor operator, and this gives you viscosity. Two viscosities, shear and bulk. We'll talk about this a little bit later. Okay? But the main principle, at least philosophically, should be clear now, right? If it is not, then please ask me to clarify. Yes?
I think there should be a comma in the combinations.
Yes. Thank you. Right. Yep.
In the external field part, do we take, for instance, changing magnetic fields generates electric field also? Those
Yes.
Or is it just a constant?
You can cook up, so the external field you can cook up in order to measure whatever, for example, you may have system which is anisotropic, right? And it will have transport coefficients different in all directions, right? So the thing will flow, for example, along X, it will be something, along Y, it will be different, and so on, right? So this is in your hands. You are an experimentalist, right? So I mean, you're not, but suppose you're an experimentalist, right? This lambda is in your head, in your hand. So the same with gravitational wave, right? So we will see later on how to pick up a polarization of gravitational wave in order to measure, for example, only shear viscosity, not the bulk, and vice versa, right? Okay, so this is in your hand. Other questions? All right, fine. So, so this is all tools we ever need in order to proceed. And let me. It's very tempting to. Yeah. So, okay. Let me give you one simple example. I mean, all of this works great in textbook examples. I mean, perfect, right? So in order to calculate, I'm sure you have seen this before, right? So compute, for example, thermodynamics of something, right? You have a gas. Okay, let me just mention this example because it's so satisfying to see something computed until the end that it's very difficult. But so these are two tools, right? So linear response and Z. and Z. This is all we need. Right, so I just remind you this fantastic calculation. So this is, you have, for example, n diatomic molecules. Right, so you have something like this. This is your model of your gas, this little dumbbell, right, and then it can just go straight, or it can rotate, for example, or it can oscillate, so all sorts of motion is possible, and you model some diatomic gas, like, for example, N2 or 2 or whatever you want, right? It's perfectly fine. So in principle, you can you can write down the, I don't know, the Hamiltonian, right? The Hamiltonian of the system will be the sum of p squared I over 2m plus h interaction. And suppose, yeah, so this is already quite complicated, but of course, in principle, you have to add the interaction between various molecules. They do interact, they collide, for example, right, and so on. So there is another dumbbell somewhere on a collision course. So they collide. And then, so you don't really know. I mean, this Hamiltonian is completely hopeless. I mean, there is no way you can, even with some reasonable interaction Uij, there is no way you can compute everything from first principles already in this simple system. So what can you do? Well, you say, well, the gas is sufficiently dilute, maybe it doesn't really interact that much, so let's do this, okay? And then it converts it into ideal gas. All right, so this becomes ideal gas. Fine. Step number one. And ideal gas is still sufficiently complicated because the interaction Hamiltonian contains three. So interaction Hamiltonian will contain rotation plus oscillations plus some electron transition inside the molecules plus so on, right? So this is already sufficiently complicated. So let's focus, for example, on oscillatory part. All right, the oscillatory part, again, this is a very crude model of rather complicated vibrations right inside the molecule. So you say, well, let's approximate it by harmonic oscillator. Only harmonic motion. And then you say, great, oh, I know what to do, right? So my Z, so the goal is always to compute Z. So my Z interaction will be the product of Z rotation, Z oscillations, and Z whatever is else, right, electrons, right, for example, times whatever else is there. And I know how to compute Z oscillations because I know perfectly well how to do this. So this is trace rho, and rho is given by the sum of, so trace is the sum of all quantum states, e to the minus beta h, but h is just a harmonic oscillator, so this is minus beta h oscillator acting on these ends. And we all know, now this is a crucial moment, right? We know perfectly well what happens with this, right? And therefore, the spectrum is known, so the eigenvalues are simply known, and you can substitute it here, do the computation, and it gives you a fantastic result. So this n is just a sum from 0 to infinity, e to the minus beta h bar omega n, e to the, well, there is a prefactor, h bar omega over 2, and this is all 1 divided by 2 sinh, this is just a geometric progression, omega over 2, right? So if you know the properties of your molecule, of the dumbbell, right, of this eigenfrequency omega, then you can compute a partition function from first principles, and therefore you can compute all thermodynamics which is related to this part of motion. All right? So this is one of the very few examples where actually partition function can be computed to the end from first principles. It never happens in real systems. So unfortunately, you have to do various approximations, and you can see even here you have done quite a bit of approximation. So you may ask, what happens if you take into account interactions, what happens if this motion is actually anharmonic motion, and so on and so forth. So even for this very simple example, for dilute gas, you can you see that this is already quite difficult. So, so this is a machinery. Again, you compute Z, and the second is linear response. To get transport. But the machinery is fine, but then you need to implement it in practice. When you try to implement it in practice, you encounter various difficulties, and these difficulties are mostly related to the fact that you don't know the exact spectrum in your microscopic Hamiltonian, your system. You cannot solve it exactly unless you have something completely simple. Now, how about transport? We have a great tool for transport. In order to implement this program here, we have a great tool which works for sufficiently dilute gases. And that has been developed by people like Maxwell and Boltzmann, and also people in the 20th century who taught us how to solve Boltzmann equation. And this is a very complicated mathematical theory. But this theory actually is quite successful. You can, using kinetic equation, kinetic theory, Boltzmann equation, you can predict with sufficiently good precision viscosity of air in this room. Then you do experiment, and the results will coincide, more or less. You cannot, using kinetic theory, to predict viscosity of water. It fails. It fails because water is not a dilute system. You have no small parameter to expand. You can apply kinetic theory and Boltzmann equation only because you can throw away most of these interactions from here. So those of you who are familiar with BBGKY chain, right? So the kinetic theory is a large subject, which we will not, of course, touch in any detail, but it's a hyperlink for you. So please learn the fundamentals of kinetic theory, and please understand one thing, that kinetic theory, and Boltzmann equation in particular, is an approximation which is made with respect to a full microscopic description of the system. And the magic words to learn here is so this is a magic abbreviation which starts with Bogolyubov, but ask me later if you are interested in detail. It's important to understand that kinetic theory, as we know it, is an approximation to a real system. But suppose we want really to develop some microscopic tools to implement. We have a tool, right? But we want to implement it. How to use our linear response in a system which is not dilute, which is not a gas. So suppose we want liquid. And maybe we even more want quantum liquid, right? So because quark-gluon plasma, which I'm about to describe now, maybe after the break. Will you tell me when? After? Yeah. Okay. So, so systems like quark-gluon plasma are not dilute at all. So these are quantum strongly interacting systems, and this strong interaction makes it impossible to apply. So let me, instead of cryptic kinetic theory, like this. Okay, I want to stress. I'm not saying this maybe well enough, but I just want to stress one thing. I encountered in my life a number of people, very good professionals, who for some reason believe that kinetic theory is a theory in itself, in the sense that it is fundamental, right? It doesn't, there is no approximation involved and things like that. It's very strange, but it's yeah, please don't do it. The important thing to learn is how, from full microscopic description, from full Hamiltonian, from complete set of equations of motion, in a certain approximation, which is well defined, you can get Boltzmann equation and kinetic equations. It is an approximation, all right? It is an approximation which happily breaks when you want to describe things like water, not to mention things like quark-gluon plasma. All right, so I think it's a good time to make a break, and then we'll come back to quark-gluon plasma in the second half today. If you have questions, please feel free to ask me during the break.